This video is going to explain how to solve systems of nonlinear equations and inequalities. This video is specifically going to work on solving nonlinear equations, and then another video will be talking about systems of nonlinear inequalities. The first part I want to explain is how to work on solving systems of linear equations, just remembering how to actually do them. And I'll also write out how to solve the systems of inequalities on this page as well. So the steps for solving the systems of nonlinear equations. So for equations, what it means for nonlinear, it means that it's not just two lines intersecting. Nonlinear could be a parabola, a radical, an inverse function, an exponential function, anything that has an equation that is not linear. It could have a parabola and a line, but one of the equations is not linear, so that means it is a nonlinear system. So for equations, we still do the same steps that we've always done. We still want to get our equations in y1 equals and our y2 equals. We've got to put them into the correct format. Then we're going to graph. We're going to press graph so that we can see, to see the intersection or intersections, because there might be multiple ones now that we're dealing with nonlinear. Once we see how many intersections there are and where they're located, we're going to press second, trace 5, which is the intersection, and then we're going to move our cursor to that intersection, or to one of the intersections. Then once we get to the intersection, we're going to press enter 3 times. Now if there are multiple intersections, then we're going to need to go back to second trace 5, go to the other intersection, and then press enter 3 times again. And we do that as many times as there are 4 intersections. I'm also going to write out some of the steps for the inequalities to solve systems of inequalities. For inequalities, we still want to graph them. We're actually going to graph the inequalities. Graph inequalities on a coordinate plane. Using tables. Now we can graph them in our calculator and get the coordinates so that we can graph them on the coordinate plane. Then we're going to make sure that we use dashed or solid lines accordingly. Use dashed or solid lines accordingly. Remember, inequalities are less than, greater than, less than or equal to, or greater than or equal to. So the dashed lines are when it's less than or greater than. Solid lines come from less than or equal to, greater than or equal to. Once we have everything graphed, then we're going to shade accordingly for both graphs. So again, if it's greater than or equal to, we're going to shade up from the graph. If it says less than or equal to, we're going to shade down from the graph. Once we've shaded both of them, we're going to find the intersection of the shading. This is going to be called our solution set. Because inequalities have multiple answers, we could have multiple numbers inside of our solution set. So again, I'm going to work on solving the systems of nonlinear equations first. So I will need to use a calculator. I need to get a graphing calculator, and I need to make sure that all my equations are in the setup of y equals. So I'm going to put this down. I'm going to do these 8 examples. The first example says systems of nonlinear equations. Examples. Write solution or solutions as coordinates. So we're going to still do everything in our calculator, but we do have to make sure that we write our answers as coordinates. The first question is y equals x squared and y equals 8 minus x squared. Now these are both already in y equals format, so these we can already go ahead and put into our calculator. So I'm going to get my calculator, turn it on, go to y equals, I'm going to type in x squared, and then on the second one, I'm going to put 8 minus x squared. I do not have to necessarily get these into standard form. I just have to make sure my y is by itself, and I plug these in correctly. Now I'm going to press graph to make sure I can see my intersections. And before I press graph, I'm actually going to press zoom 6. Zoom 6 is that standard window. It'll be a right 10, left 10, down 10, and up 10. And then we can change that from there. But I want to look at a standard window first, and then I can zoom out if needed. I'll press zoom 6. There's the first parabola. There's the second parabola. And this was a minus x squared, so it is going down. But you can tell that the first parabola and the second parabola will actually intersect twice. So I'm going to make a note of that the graphs cross twice, so there are going to be two solutions. Graphs cross twice. It means there are two solutions. So we're going to go find them. So in order to go find them, we press second, trace. We want number 5 for the intersection. Now my cursor is blinking right here at 0, 0, so I'm going to move it to the left or right to get to one of these intersections. So I'll move it to the left till I get to this intersection roughly right there. Then once I'm at the intersection, I can press enter 3 times. Enter, enter, enter. The first intersection is at -2, 4. This is a coordinate of -2, 4. It does need to be in parentheses for it to be an actual solution. Now if we go find the second one, I need to do second, trace 5 again. But this time I need to go to the right-hand side to get to that intersection. So I just hold the right arrow key down until I get to the intersection. I'm roughly there. So I'm going to press enter 3 times. Enter, enter, enter. We get at x equals 2 and x equals 4. X equals 2 and y equals 4. So the coordinate, so we can say and 2, 4. Those are our two intersections. We have our two coordinates, so we can highlight our answers, saying that these are in fact our solutions. And you can check them by plugging them back into the equation. -2 squared is positive 4. And again, -2 squared is positive 4, so it's 8 minus 4 is equal to 4. Do the same thing here. 2 squared is equal to 4. 2 squared is 4. It says 8 minus 4 is supposed to be 4. So then that is correct. On this next problem, they are also already in y equals format, so we can go ahead and plug them in. So we go to y equals, so I'm going to clear these out. I'm going to type in x squared plus 3x plus 2. Go down to y2, put 2x plus 3. Now this is a parabola and this is a line, but because we have one of them that is nonlinear, this is called a nonlinear system of equations. So technically I'm still in zoom 6, so I can just press graph. Here's our parabola, and there's our line. Now you can see that it did go through and then come back out, so there should be two intersections here as well. If you're not sure about how many intersections there are, you can zoom into it to see if it does cross through, and on this one it will, so we can go find both of these intersections. I'm going to press second, trace 5, and my cursor is blinking right here, and it's really close to one of the intersections, so I'll just press right until I get to that intersection. Once I'm at the intersection, I press enter 3 times. Enter, enter, enter. And this one is at a decimal, so it looks to be at, x is at 62 hundredths, because that 8 makes up 1 and 2, comma 4 and 24 hundredths. So I'm going to write my coordinate. This is 0 and 62 hundredths, comma 4 and 24 hundredths. That's our first intersection. So go to second, trace 5, and go to the left, follow that curve, and it looks like about in that area. So once we get to that area, we're going to press enter 3 times, enter, enter, enter. And the cursor stayed at that intersection, intersects at -1 and 62/100, and then at -24/100. So we can say and -1 and 62/100, comma, -24/100. Those are two solutions, so we can highlight them. Now, these are rounded answers, so plugging them back into the equations would not give us exact answers, but they would be relatively close. Number 3 is also in y equals format already, so we can go to y equals. This is a parabola and another parabola. So we have clear these out. We have 2x squared plus 3x plus 4. Go down. We have x squared plus 2x plus 3. Again, I'm still in Zoom 6, so I don't have to press that again. I can just press graph. Here comes our first parabola. Here comes our second parabola. Now, it looks like it might intersect right in there, but if I zoom in, so I'm going to press 2, but notice that the graph didn't change. I actually want to zoom in this area where I think it might be intersecting. Zoom in right here. There's our first parabola. And there's our second parabola. And they're actually not intersecting right there. So if I go back to Zoom 6, first parabola, second parabola. Now my first parabola will keep going up, and my second parabola will keep going up and out as well. So these actually will never intersect. This first one with the 2x squared is actually going at a vertical stretch of 2, so it's actually staying closer together, whereas the x squared is at a normal pace, so it's staying up and out as well. So those actually will never intersect, and that's okay. So that means that the solution for this one is there is no solution. Because again, a solution for a system is where they intersect. That means that, so if I write it like this, so 0 with a slash through it, this means no solution. This does not mean 0. This means that the parabolas don't cross for this problem. The parabolas don't cross because there was no solution. And again, that's okay to have no solution. If they were the exact same parabolas, they would have infinitely many solutions. So we can also have no solutions just like in lines. On number 4, we have a line and a quadratic as well. So we're going to clear these out. These are already in y equals format, so that's good. We can put in the first one, 1/2. Now, a fraction should always have parentheses around it, just to keep them connected. X minus 5. And then on the second one, it's x squared plus 2x minus 15. Again, I'm going to press graph because I'm still in Zoom. I went back to Zoom 6, so I'm going to press graph. There's our line. And there is our parabola. Now, the parabola did go all the way down and then comes back up. We can see that it crosses in 2 locations. We don't have to see the entire parabola to see this. So we can find our 2 solutions here. Second, trace 5. I'm right here, so I'm going to go to the right to get to this intersection. Press right. And as long as I'm close to that intersection, I should be good. So I'm going to press enter 3 times. Enter, enter, enter. So this intersection is at 2.5 and -3 3/4. So our first intersection is at 2.5, comma, -3 7/500 or -3 3/4. Now you can't see the intersection over here because the words are covering it up, but we remember that the intersection was also over here. That's why we want to look at the graph before we do anything, because we want to see how many times it does cross. So I want to go and find this intersection as well. So I need to go back and press second, trace 5, but this time I need to move my cursor to the left. Just hold it down to the left. Once I get to about where I roughly remembered where it was, I can press enter 3 times. Enter, enter, enter. And if you notice throughout this, the cursor kind of stays in the same location because we're at that intersection. So the intersection here is at -4 and -7. So we can say and, parentheses, -4, -7, parentheses. These are our two solutions for here. Now all four of these had quadratics in them. Those are with parabolas. They're a little bit easier to see and a little bit easier to use because the parabolas are nice and U-shaped. These had two solutions. This one had two solutions. This one had none because the parabolas didn't cross. This one had two parabolas, a parabola and a line, two parabolas, a parabola and a line. Just because it has two parabolas does not automatically mean there's not going to be a solution, because this one did. This first one had two parabolas and it had two solutions. But you do need to make sure that if they are not crossing, that you do put no solution. These next four are actually slightly different. These will not necessarily be only quadratics. They can be different types of functions like inverse and radicals, but we're also going to have potentially linear and quadratics in it. So number 5, we have x, y equals 1. The problem with this is that this is not in y equals format. We need to make sure that we get this equal to a y. So on this one, the x is multiplied to the y. What that means is that we actually have to divide by that x. So I'm going to circle this x, so that's what we're dividing by. So in orange, I'm going to write out what the actual equation when I say y equals 1 over x, 1 divided by x. On the second equation, we also don't have it equal to y. We have to move this x over as well, but this time it's a positive x added to the y. So we have to subtract the x because this is a positive x, so we subtract the x from this 2. So our equation is actually y equals 2 minus x. And again, you don't have to put it into standard form. Now, from the first equation, we still always want to keep our first part in parentheses. So our numerator is in parentheses on here. So if I go to my y equals, I still have them from my last equation, so I'm going to go to y equals and clear them out. I'm going to put parentheses, 1, close parentheses, divided by x. Down the second one, I'm going to put 2 minus x, 2 minus x. And again, we want to press graph because this is a new type of equation we haven't seen before. I'm going to press graph to see what it looks like. Here's the 1 divided by x, so it's split apart, and then there's our line. So if you look, our line looks like it's only crossing around this section of our graph and not this one. So in this case, I might actually want to just zoom in on this location. So I press zoom 2, and I actually want to move my cursor to this area so I can zoom in on that location specifically. So I can see that it might be touching it, might not necessarily be crossing through. So let's see if we can find this. So second, trace 5. All right, so our equation says 1 over x, so that's this part of the graph, and it's on that intersection, so I'm going to press enter. And it goes to the line. I'm still on that graph, the intersection. I'm going to press enter again. I'll press enter a third time. Let's see if it works. It's still loading. Okay, it says iterations, error iterations. What that might mean is that I'm not zoomed in enough. I can see that it looks like it's crossing, so I'm going to go back to my graph. I'm actually going to zoom in again on that location. So zoom 2. I'm going to zoom in on this location again. There's my inverse. There's my line. So I'm going to press second, trace 5 again. I'm going to get to this area. Enter, enter, enter. See if it works this time. It does. So the intersection is at 0.9999. That would round to a 1. And then this one is 1.0, all those zeros 6. So it would be a 1 as well. So intersection here is at 1, 1. If we go back to zoom 6, so I can look at the entire graph again, I had two parts of the first equation, but then the second equation was the line, and it looks like it's only touching. So that's why there's only one answer, because it's just touching it at that location. So if you get an error and it says iterations, that might mean just zoom in further onto that graph, because if you notice on that the first time I zoomed in, I still had part of a graph on this side, then I had the zoomed in section over here, but I still had that little section over here that wasn't part of our solution. Number 6, we have y equals the square root of x plus 1. So this time we do have a radical. This is also different. But then we have y equals x minus 9. These are both in y equals format, so I can go ahead and put them in. Y equals, I have the square root of x plus 1. So when we do this, square root, that x plus 1, both of those are inside the radical. So my calculator opened up a parenthesis when I pressed square root. I need to make sure that x plus 1 is inside that radical. So I close my parentheses because all of that is inside the radical. And then in the second one is x minus 9. And again, I want to press graph to see what it looks like. There's the radical. And there's the line. Now, right now, it doesn't look like they're crossing. But we know that lines go on forever. So if a line kept going, it would end up crossing that radical somewhere over in here. Let's zoom out of that so we can see it. So zoom 3. Now actually I can see that it's going to cross somewhere over here. So I'm going to press my right arrow key, go all the way to the right, and zoom out from over here. I'm going to press the right arrow key, and still I can't go any further, and then I'm going to press enter. There's that radical, and there's that line. So it looks like they are crossing at least once. And the line will keep going up, and the radical is slowly going this way. It's still going up, but not as fast, so it will never cross again. So we just need to find that one solution. So second trace 5. We're going to move our cursor until we get to the general location of that. We're going to press enter 3 times. Enter, enter, enter. And we're at 12 and 7/10 and 3 and 7/10. So we can put 12, we can also say 12 and 70 hundredths. So 12 and 70 hundredths, comma, 3 and 70 hundredths, which is also 3 and 7/10. And that is our one solution for this problem. Because that line and radical will never cross again. On number 7, we have y equals 4 over x and y equals negative x plus 8. Now this is linear. This is a different type of equation than we saw this one on number 5, something like that. So we know it's going to be split apart like number 5 was. So go to y equals. They're both in y equals format, so we can go ahead and type them in. So we type in 4 divided by x as you see it, and then negative x plus 8. Now again, if you have the newer calculator and you did the alpha y equals on that one, that's perfectly fine. My calculator, if I do alpha y equals, doesn't do anything. So I can't put it as a fraction like the newer calculators can. I'm going to press zoom, because I was zoomed out, I'm going to press zoom 6, because I didn't do that again. There's that first one, that split apart graph, and then there's the line. So now the line is actually crossing this half of the graph twice. So I need to find both of those. Now if I try second trace 5 right now, do you notice that you can't see your cursor? And it says x equals 0, y equals nothing. Well, that means that the x right here, this is called an asymptote. It's not actually on the graph yet. But I do know that I want to go to the right-hand side because it's on the right-hand side of the y-axis. So I'm going to press right, and here comes our cursor. So if I had pressed left, it would actually have gone on the second half of the graph. So if I wanted to press right so I could get to this location. Now this is probably as close as I can get to that first intersection. So I'm going to try and press enter 3 times on this one and see if there's any iterations problem again. So enter, enter, enter. There was no iteration problem, so I can write down my solution. This is at 54 hundredths and 7 and 46 hundredths. So 54 hundredths and 7 and 46 hundredths. But there is a second one, so I'm going to go back to second trace 5. My cursor is still in this area that I was originally, so I'm going to keep pressing right to get to this other intersection. Once I'm there, I can press enter 3 times. Enter, enter, enter. I'm at 7 and 46 hundredths and then 54 hundredths. So it's actually inverse of that. So we have 7 and 46 hundredths, comma, 0 and 54 hundredths. Those are our two solutions for these equations. With the word and. And this last one on systems of nonlinear equations is y equals negative square root of x, and then we have negative x squared plus 7x plus y equals 3. Now, my y is not alone, but do you notice that there's nothing multiplied to the y? That means I just need to take all of this and move it to the other side by doing addition or subtraction. So when I rewrite this, I'm going to have y equals, I keep my 3 because I didn't have to change that. And again, it does not have to be in standard form since I'm using my calculator. I need to move both of these, but when you move them across equals, they change sign. You do the inverse. So this becomes a positive x squared. This becomes a negative 7x. Now I can graph both of these. Let's go back to my y equals, clear out both of these. I have negative square root, which is located here, second x squared right here, and then x, close parentheses. Go down, I have 3 plus x squared minus 7x. And I was in Zoom 6 still, so I'm going to press graph. There's the square root, and there's the parabola. Now, I can definitely see that it's crossing here once, but the question is it also crossing there? It looks like it is, so we can definitely check. So second trace 5, and my cursor, I'm going to move it around here. I'm going to press enter 3 times to see if it works. Enter, enter, enter. And it does. The cursor stayed here, so it's telling us that the intersection is at 59 hundredths and negative 77 hundredths. So our first intersection is at 59 hundredths and negative 77 hundredths. But then we definitely have another one over here, so I can go ahead and put and. So the second one is second trace 5. Going to keep going on your cursor, so right until we get to this area right here. And we'll press enter 3 times. Enter, enter, enter. And it's at 6 and 1/10, comma, negative 2 and 47 hundredths. So we have 6 and 1/10 or 10 hundredths, comma, negative 2 and 47 hundredths. And those were our two intersections. This was systems of nonlinear equations because they weren't just two lines, which is one of the reasons why they can cross multiple times. Most of these crossed at least twice. We had one that didn't cross at all, and we had one that just bounced off of it or touched the graph instead of crossing through. So we do the same steps as we've always done, second trace 5, but we just find the multiple solutions. And we still have to get them into y equals format, so any way you want to. Again, it does not have to necessarily be in standard form, but you do have to have them in y equals.